All right, this is 7.22. We're going to wrap up Chapter 7 using the laws of universal gravitation. Today we are going to look at different types of mass. There's two different ways to calculate mass. One is inertial mass, so mass due to movement, and the other is gravitational mass. We're going to talk about the gravitational field. Instead of thinking of gravity as just 9.8, we're going to talk about it more as you get further away, it gets lighter and lighter, so we talk about it as a field. And that will lead us to Einstein's gravitational theory. So, acceleration due to gravity. The weight that you feel is just the force that counteracts gravity. So that is the floor pushing back up on you, right? So basically, you're attracted to the Earth, and the Earth is attracted to you, but the only reason you feel heavy is because you have this floor pushing on you. If you didn't have the floor and you were just in free fall, and there's no air around you, you would feel weightless. So it's this floor pushing up on you that you feel, that makes you feel like you're heavy. In space, when you're up there in the nice orbit, gravity's about 8.6 meters per second squared. It's not disappearing. So it's not that you're necessarily weightless. You feel weightless, but it's because the craft is falling at the same rate around you as you are falling. You and the craft are both falling at 8.6 meters per second. So since it's falling and you're falling, you don't have this floor pushing back up on top of you in order to feel that weight. So you don't feel weight. You feel weightless, even though there's still a force acting on you, this 8.6. And that's because you are falling around the Earth as the spacecraft is falling around the Earth. And by falling around the Earth, I mean orbiting, right? It's just that constant falling. Let's draw a picture of that. Here is the Earth, right? And then you're falling. You have so much velocity that you're falling. But as you're falling around the Earth is curving away from your path because the Earth is round. If the Earth was flat, eventually you would fall down into it because it's a parabolic path. But since it's round and you have enough velocity to keep going, you're going to continue to fall around the Earth. So the further out you go, the less gravity is going to affect you. You're still going to feel a pull. Even if you're across the universe, you're still going to feel a pull from the Earth. It's just that there's a lot of other things that are bigger and closer to you that you're going to feel a stronger pull. Do you have a question?
That was my question.
Okay, yeah. So it doesn't really matter. And that comes from the equation that we get from Newton's law of gravity, F equals gmm over r squared. So this r squared is just that distance. So you're going to feel a force of the Earth no matter where you are in the universe. It's just going to be really, really, really small. You're going to feel a force of this gravitational duct, right? This duct right here is going to pull on you. It's pulling on you right now. It's just really small compared to that of the Earth that it's practically negligible. Right? We can pretty much ignore it because it's so small because the Earth is so much bigger. So yes, you are attracted to this duct right here. How does that make you feel? Okay. All right, so it's basically the thing that makes you feel weight is something that's counteracting your falling. And if you don't have anything counteracting your falling, you're not going to feel like you have weight, even though you are still being, you still have force on you. So that'd be basically if you're falling through the air, the reason that you still feel like you have weight is because the wind is pushing against you. But if there was no wind, if you were falling on the moon, you would feel pretty much weightless. Okay, I still see a red cup right there. And I think everybody, you got a red cup out too. So does that mean you want me to stop? Okay. There we go. All right, how about that one?
Just cover it. Or something.
Just cover it. There you go. It's per table, so both of you guys are in charge of that. All right, gravitational field. Gravitational field is used to explain the pull between two objects. So you can think of it as a field. The closer you are to the object, the stronger the field. The further away from the object, the less the field. It's not like an imaginary line. It's kind of an area. As you get closer, it's stronger, like the pull of a magnet. You can still feel it, and as it gets closer, it starts to stick together or push apart. So the closer you are, the bigger the vectors are, the bigger the force vectors on the gravitational field, and the further away you are, the smaller these vectors get. So as this object moves closer and closer, it feels a stronger force, meaning that the acceleration is going to go up. And that comes from playing the arrow game with F equals ma. Your mass isn't changing at all. So as you get closer, your force is going to increase, which means your acceleration is going to increase. And that acceleration due to gravity on the surface is 9.8, but out in orbit it's like 8.6. So as you get closer, that 8.6 is going to start growing up to the 9.8 until you hit the surface. So it increases as you get closer. The direction always points straight towards the mass. So if you are here, it's going to point towards the center, so it's going to be the left. If you're here, it's going to point down. If it's here, you're going to point right, and if it's on the bottom, it's going to point up. It always points towards the center of mass. We just usually in our problems think about it always going down because we're standing on the surface of the Earth. So down is always towards the center of the Earth for us. We can get this gravitational field G by using this equation. G equals the gravitational constant times the mass over r squared. Let's see where that comes from. Again, this is another proof. You don't really need it, but it's kind of interesting. We're going to use the force you feel, mg, and this equation right here. We're going to put them together since the force you feel, basically your weight, is the same as, this and this. So all we have to do is set these two forces equal to each other. So we get mg. This is, remember, the mass of u. And in this equation, you have the mass of u and the mass of, let's say, the Earth. And this is over r squared. So your distance. In this case, this is going to be the radius of the Earth. And this, your distance from the Earth. So the weight of u, mg, is going to cancel on both sides. You're left with g equals gravitational constant g, the mass of the Earth over r squared. So in this equation, they're always talking about the mass that you're on. So you want to find Jupiter, you need to know the radius of Jupiter and the mass of Jupiter. And you'll know that Jupiter's is like 26.1 or something like that, 27 meters per second squared on the surface of Jupiter. For here, if you plug in the mass of the Earth into m and the radius of Earth into r, you're going to get 9.8. Don't forget that the gravitational constant is 6.67 times 10 to the negative 11, and those are all units you can ignore. Yeah, it's all units. Okay, let's see. Check our cups. You done? Good? Okay, good. All right. So there's two different types of mass using F equals ma and this F, Newton's law of gravity thing. The first one says if there's a net force on you, you have to have some sort of inertial mass. This is an inertial mass due to acceleration. The other mass is a gravitational mass, and that is mass due to gravitation. In both cases, it doesn't matter whether it is mass due to acceleration or mass due to gravity, because gravity is a force, right? And force is acceleration. So these two masses, even though they can be calculated different ways, they're exact same mass. So inertial mass and gravitational mass are exactly the same thing. It's just one is through movement and one is through gravitational pull. So kind of an idea of this is when you're spun around in a circle, like the astronauts, they have to go through that thing where it spins them around in the circle to, it's kind of like a centrifuge, but for a person. I don't remember what they're called. No? Anyways, it smashes them up against the wall. That is inertial mass, because it's flinging them to the outside, and that makes them feel really heavy. Well, that hasn't really changed their mass, it's changed their force and their acceleration. But that you can calculate an inertial mass. Versus here, gravitational pull, just we have like a really big mass object, so it's not due to the spinning part or the acceleration of the spinning part. Instead, it's due to just mass attracting other mass. And that mass, either way you calculate it, is the same mass. Your mass isn't going to change. So by moving really fast, you have mass. And by having a force act on you, also mass. Same mass. And I know this seems kind of dumb because you're like, okay, mass is mass, but It's like a big thing in physics for some reason. Okay, see if I cut it. So, Einstein's gravitational theory, our last little bit that we're going to talk about. Einstein created this idea of space-time fabric. So basically, the more massive it is, the more it bends this fabric. I'm really bad at drawing these pictures, but we'll do our best here. Basically, imagine this is the sun, and we can take the orbit off of it. We don't need that. And since the sun is really, really big, imagine it's sitting on a sheet. And since it's like a bowling ball sitting on a sheet, it's going to warp that sheet. Well, if you give a marble some velocity so that it orbits around the sun like this, it's not going to go directly into the sun because it has velocity. And it's going to warp this space-time fabric just a little bit, like that. And it's going to go around, kind of like the water does around a drain, because it has velocity and it circles it. I mean, that's a little bit different, but it's the same kind of idea. Or those roulette wheels you always see in the movies. Not the roulette wheels, where they take the ball and they spin it around and they pick a number and then it lands in a slot. Well, it doesn't slow down until friction slows it down enough and then it falls in the slot. But it'll keep going around there if there was no friction. So this, if we give it a little bit of velocity, it's going to orbit around the bowling ball. And it's going to bend this sheet just a little tiny bit when it does that. And if we had another way of, like the moon, having some velocity, and it was really, really tiny, like smaller than the size of a pea, it would, and we gave it velocity, it would start to orbit around this thing because it's bending the space-time fabric in that area. And it would be, the squish or orbit just a little bit as it comes to the sun. It's not going to be perfectly circular because the sun is pulling on the moon as well. But the moon is really, really close to the Earth, so it's going to orbit more around the Earth. But it bends this sheet. And it kind of, the way that Einstein figured this out is he was looking at light from other objects. And you notice that the light actually bent around things with gravitational mass. So it would bend around like black holes and stuff. So this space-time fabric allowed him to kind of connect light, which is the electromagnetic theory, with gravitational stuff, sort of. But he did find that light was bent by gravitational fields. And anytime he tried to put electromagnetic stuff with what he called general relativity, it would break down. So he was just trying to figure out how that worked. And he kind of did this space-time fabric. They're still working on it. String theory was kind of like 10 years ago. They were talking about string theory. Now they're talking about the standard model where each of these things is particles. But they still haven't really completed the theory. They're not perfect yet. They're still searching for some particles. But basically, in the space-time fabric, he was talking about this led to black holes. So black holes have so much mass that they're actually more like a pinpoint in the space-time fabric, where they actually break into it. And that allows the theory to come up with wormholes and things. So it has so much mass that it actually breaks it. Now again, there's a lot of theories around black holes. I don't know all of the theories, so you might have heard stuff that I didn't hear, but that's kind of the general idea, is it has so much mass it actually breaks through this space-time fabric. Now where it's basically mass that's 20 times the size of our sun is broken down into about a 10-mile radius. Really, 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 really dense. It's really dense. And it's so dense that it's supposedly breaking through these space-time fabric things. And I guess some of the theories are if it's spinning, it could be a wormhole, things like that. Some of the theories lead towards that. Depends on how you do the math. So it is very complicated. I don't know the answers to your questions. I know that you're going to have lots of questions. So I don't know. I told you everything I know. Okay, so basically what happens with this space-time fabric, it's affecting light. And it's saying that as you get closer to things that are super gravitational, it actually slows time down. So here we are experiencing a slower amount of time than people up in airplanes in space because they're further away from the gravitational field. So if you were able to get really far away from any sort of gravitational pull, your time is actually going to be faster. So you're going to look at people on the Earth and they're going to age like super, super slow because their time is slowed down. Or you are going to be a little bit faster. Same thing with velocity. The faster you go, I believe the slower the time. Okay. Or the other way around. So here's a picture of space-time fabric. You can see that the sun is bending the space-time fabric. And since it's bending space and time, again, the closer you are to the sun, the slower you're going to experience time. Something that's kind of interesting I really liked when I was in college learning about this stuff, is that if you were watching someone from a black hole from like Earth, it would look like it took millions and millions of years. But the person in the black hole, it's going to happen in an instant.
Say that one more time.
We're watching a person fall into the black hole from Earth. It's going to look like they're crushed to death over millions of years. If you're in the black hole, you're being sucked in at the speed of light at the black hole. So for the person in the black hole, it happens instantaneously. We from our point of view, our time is moving different than their time. So we're watching it in slow motion. But for them, it's happening instantaneously. So they experience like 1 nanosecond. We experience like 1,000,000 years. Does that make sense? So their time is slowed down compared to that of ours because we have less gravitational pull on us.
Is that kind of like when the sun explodes? Like we see it exploding?
No, that's different. That's just the time lapse from the sun happening. That's like and we're actually talking about things happening in different time areas. It's like watching the video in slow motion, except for they only experience a second. We experience 10 seconds or something because we're watching it in slow motion. But it's not that we're actually watching it in slow motion. It's that it's happening in slow motion compared to our point of view. It's a difficult concept. So gravitational pull slows things down. All right, now we have some clicker questions. Here we are. Here's our first clicker question. We have some fancy elevator here. It's carrying a person who starts to fall freely towards Earth. So the elevator and the person are falling, the same rate towards Earth, say 9.8, even though it's probably a little less than that. The contact force between the elevator and the person inside the elevator will be equal to what? Remember, the elevator and the person are falling at the same speed towards the Earth. Some of the answers might be on this one, just so you know.
I had no idea how to do 15.
Yeah, it's going to be on the back of this one. Back of this one. All right, we should have 29 people here today. 28 people. You're missing 2. So I'm missing 1, 9, 17, and 21. 21's gone. Okay. So 1 and 17. Just number 1. Okay, here we go. In this case, if the elevator is falling at the same rate as the person, there is no contact force pushing up on that, so the person should actually feel weightless. So they'll feel 0. Even though they're falling, there's nothing counteracting it. Question 2. Venus has a radius of a very large number and a mass of another large number. Calculate the value of the acceleration due to gravity on the planet's surface. You're looking for little g. What's little g? Calculate little g. Just in case you forgot what the gravitational constant is, I'll write it on the board. 6.67 times 10 to the negative 11. You're looking for little g.